It's simple, right? Air flows over the cylinders, which cools the engine. Well, that's not wrong, but there is so much more to an air-cooled engine than that, especially for aircraft engines. It's certainly not rocket science, but it is a very interesting science. We'll look at how air cooling works on a variety of engine layouts, but the main focus will be on horizontally opposed 4- and 6-cylinder engines. Just to preemptively address some comments, air-cooled engines are cooled in a few ways, not just by airflow. Oil is one of those ways, and it actively cools the engine. This is more of a factor on some engine types than others, but oil plays some role in cooling all piston engines. Hot engine oil is run through an oil cooler before being pressure fed through oil galleries. The oil cooler is cooled by airflow and can be mounted on the firewall, the front of the cowling, or somewhere inside the engine bay where it gets sufficient airflow. This cooled oil then gets pumped back into the engine. But oil cooling accounts for a relatively small overall cooling contribution in air-cooled engines. Another cooling factor is fuel. Yes, fuel cools an engine, and the pilot has direct control over the amount of fuel delivered to the intake charge via the mixture control knob. At least that is true for most Lycoming and Continental engines. Some more modern engines like the Rotax 9 series, as well as other FADEC engines, do not have manual mixture control. For those that do, enriching the mixture is something pilots can do to get more engine cooling, as excess fuel absorbs heat inside the cylinder, bringing temperatures down. As a side note, cylinder head temperatures can also be reduced by leaning the mixture when already on the lean of peak side, but that is a subject for another video. Then of course there's cooling via direct airflow, the main cooling method. Heat dissipation is a very interesting subject which I won't go into too deeply, but here's the gist of it. By manufacturing cylinders and cylinder heads with cooling fins, the fins increase the surface area in contact with airflow. The greater the surface area, the greater the cooling potential. Bigger fins means better cooling, but they also mean more weight and more drag. There is a lot to explore about ideal fin length, fin thickness, fin spacing, and heat dissipation in general, but in short, fin size is always a compromise. And here is something that weighs much less, yet effectively keeps the temperatures of these engines under control. When thinking about an air-cooled engine, you might expect that air simply flows from front to rear. For a radial engine, that is essentially what happens. Air flows around and past the cylinders as the aircraft moves forward. But on boxer or horizontally opposed engines, this is not the case. Air flowing front to rear will not cool the rear cylinders properly, because the front cylinders block most airflow before it can reach them. To cool all cylinders properly, we need air to flow top to bottom, passing through the cooling fins of every cylinder. But with the air entering the cowling at the front and flowing rearward, we need a clever trick to redirect it. The way it is achieved is through pressure differential. Air flows from high pressure to low pressure. So by creating a high pressure and low pressure area, we have control over airflow direction. Very simple in theory. And the cowling of a piston-engined airplane is specifically designed to make this happen. On a horizontally opposed engine with the cowling removed, most would have noticed the baffles in the engine compartment. What they accomplish is quite simple. A high pressure area above the cylinders and a low pressure area below. Baffles consist of a rigid aluminium section and a flexible rubber seal. The rubber presses against the upper cowling to form a seal. There are also metal baffles between the cylinders that force air to flow only through the fins and wraps around to also cool the bottom of the cylinders. As the aircraft flies, air is rammed into the cowl openings. Because the baffles greatly minimize escape routes for the air, this area becomes pressurized. The only place for air to go is through the cooling fins. This setup makes the most of the available airflow for efficient cooling. But the pressurized area above the cylinders is not the full story. There is also a low pressure area below. This is largely created by suction at the bottom rear of the cowling. As air moves past the outside of the cowling at speed, it creates suction, pulling hot air out of the cowling and sustaining that low pressure area below the engine. To increase this suction, a fixed lip or flap is fitted to the area where air exits. The bigger this flap, the more suction is created, but this also increases drag. So flap size is a compromise between cooling and drag. On higher power light aircraft, in-flight adjustable cowl flaps are employed to get the best of both worlds. When airspeed is low, like during takeoff and climb, the pilot leaves the cowl flaps open to increase cooling. In this stage of flight, the engine is working hard and producing a lot of heat, but not yet receiving full cooling from ram air. When leveling out for the cruise portion of the flight, airspeed increases, more air is rammed into the cowling, and the engine is producing less heat, so the pilot closes the cowl flaps to reduce drag. On pressure cooling, I should mention that the pressure difference between the upper and lower parts of the cowling is not all that large. You might think a higher pressure differential would always mean better cooling. And it can increase cooling, but it also increases drag. Creating higher pressure in the upper section requires much tighter sealing and reduced air leaks, which complicates design. And above a certain point, the trade-off isn't worth it, because higher pressure increases drag, and more drag reduces cruise airspeed for the same power setting, which in turn reduces ram air, which lowers cooling. But even with a moderate pressure differential, the importance of baffles becomes clear every so often when the top cowling is removed for engine inspection or maintenance and then refitted improperly. The rubber seals need to face forward into the oncoming airflow so that the airstream pushes them tightly against the cowling, forming a seal. If they end up creased or oriented the wrong way, so airflow pushes them away from the cowling instead of into it, the seal is broken. Even a marble-sized air leak will have a noticeable effect on cylinder head temperatures. A fact that's easy to underestimate until an improperly fitted cowling causes the engine to run noticeably warmer than usual. That said, there is sufficient pressure to allow a few deliberate holes for blast tubes to cool accessories like the magnetos and alternators, as well as for the oil cooler. Something also worth mentioning is engine cooling when idling on the ground or taxiing. There is very little airflow going into the engine, and it's not possible to create the needed pressure differential. The only real airflow comes from what the propeller creates. However, the engine also isn't producing much heat while sitting on the ground at idle. While it's generally not advised to sit at idle power for extended periods, the low heat produced at idle power rarely causes overheating problems. This cooling system is very effective, but that doesn't mean it's perfect. The rear cylinders usually run slightly hotter than the front row, something that's easy to see on any aircraft with digital engine monitoring and temperature probes on all cylinders. That said, with properly fitted baffles with no leaks, and assuming correct fuel flow and magneto timing and that sort of thing, genuine cooling problems are quite rare. One last point before we move on, if you'll allow me a brief rant. I often hear people say, especially in the comment section of certain videos, that liquid-cooled engines produce far more drag than air-cooled engines. And this is because of the drag created by their radiators restricting airflow. And in contrast, air-cooled engines allow almost free flow of air through the engine. With pressure cooling on light aircraft air-cooled engines, it should be clear that air doesn't simply free flow through the engine bay. There is actually quite a bit of restriction. I won't go deep into that subject in this video, but it's food for thought. Before we move on to cooling inline engines, if you like this content, please consider supporting me on Patreon, where you'll get perks like voting on video topics, access to the chat, and freedom from annoying ads and interruptions, like this one. With air cooling of horizontally opposed engines covered, I really wanted to cover inline air-cooled engines as well. In a video a few years ago, I mentioned how difficult it is to properly air-cool an inline engine, but that was met with some resistance. But I think if what we've discussed so far is understood, it should hint at why inline engines are harder to air-cool effectively. With horizontally opposed engines, air flows top to bottom through the cooling fins, and all cylinders get their share of cooling air, no cylinder really blocking another. With inline engines, clearly top to bottom flow will be useless for upright or inverted configurations. Instead, the front to rear flow of air needs to be redirected sideways through the cylinders. However, designers can't really place a large exit flap opening on one side of the cowling to create the necessary suction, as that would cause asymmetric drag and disrupt airflow around the fuselage and potentially over some control surfaces. It can have relatively flush openings at the rear, and in many cases this is exactly what is done, but suction here is limited without some sort of flap. On other inline engine planes, a flap or exit lip are placed at the bottom to create the needed suction. But this complicates airflow inside the cowling, since it negates the simple sideways redirection of air by introducing a vertical flow component. The best that can be done is to distribute air pressure as evenly as possible from front to rear, while ensuring air flows around the cylinder cooling fins rather than just streaming rearward. This can be achieved with an air inlet on one side of the cowling and a baffle or air tunnel covering all 4 or 6 cylinders on that side, as well as baffles between the individual cylinders to help force air through the fins and around the cylinders. Though this varies from engine to engine and aircraft to aircraft. On the Ranger 6440 or L440, combined with corrugated internal baffling on one side is used to distribute pressure relatively evenly through the cooling fins of all cylinders, and this apparently worked quite well. It's worth noting that nearly all aircraft with inline air-cooled engines experience some degree of rear cylinder cooling problems. To be clear, this does not necessarily mean rear cylinders constantly overheat. It means that in certain conditions, rear cylinder cooling is insufficient and the pilot needs to take action to keep temperatures under control. On a hot summer's day during takeoff, for example, the pilot may need to reduce power in the climb to lower heat generation, or reduce the rate of climb to increase airspeed and improve cooling airflow. That said, I don't want to make blanket statements. The severity of rear cylinder cooling problems varies quite a bit between different engines and installations. And it's far from impossible to air-cool inline engines. There are many aircraft that do it. Virtually no modern inline air-cooled examples exist. The most modern is LOM Praha's range of air-cooled inline 4s and 6s. The design was previously with Avia and before that with Walter. But there are many from the 1920s to the 1950s or thereabouts, with de Havilland's Gypsy Major and Gypsy 6 engines as popular examples that are still around today, powering the likes of Tiger Moths, Chipmunks and Rapides. And that is all I have for you on air cooling. I hope it was informative. Thanks for watching and I'll see you in the next one.